the YouTube channel Placement Badshah, and in the last video we have discussed about how to recover the binary search tree using the in-order traversal, that is using the recursion. But in case of recursion, there is an inbuilt stack which is being used, and if the inbuilt stack is being used, okay, the average space complexity will be O of log n, and in order to avoid this, we will use a method called as the Morris traversal, and using the Morris traversal, so we can regenerate the binary search tree, and by regenerating the binary search tree using the Morris traversal, the space complexity is going to be just O of 1, that means it is going to be in the constant space. So that's cleared. And now let us see how can we do this Morris traversal. So I am just going to explain the basic thing. So if you want to know what the question is, you have to watch the previous video, okay, that is the recovering the binary search tree using the recursion method. And in this thing I am going to explain the same with the help of the Morris tree traversal, and okay, so just the basic of the Morris tree traversal will be explained here. And if you want to learn the Morris in-order traversal in detail, then you can watch the video which is being present in the tree playlist. So you just click on my channel, go to the tree playlist, and in the tree series playlist you can find all the traversals, and that is O of n, time complexity 1, recursion, Morris traversal, everything you can find. You can just watch if you want. So in the case of Morris traversal, what we will do, so first we will point on this element, and before traversing from 1 to 2, we will create a link from the 4 to 1, and then we will move on to the second node, and before moving from 2 to 3, we will create a link from 3 to 2, and then we will move to 3. So why we are creating the links means, okay, in the tree we have to, after traversing in a particular direction, we have to retrace back, and then we have to traverse the tree. In order to retrace the tree, so we were using the stack, like, okay, so if we were at 1, so we will push the 1 here, and then okay, so we will move on to 2, and we will push the 2 into the stack, and then we will push the 3. So if you want the reference, you can just pop out that element and you can get the reference. But in this case, in order to maintain the constant time, so we are using the concept of threaded binary tree. So we will create the pointer from the left child to its parent. So from the left child to its parent, from the left child to the parent. So here, okay, in order to create the links, there is a trick or a technique. So in order to understand that, so we will just write the in order traversal first. So that is 6, 4, 5. So here the parent node will be 1, 2, 1, and then 4. So we have to create the link to this 2 from its in order predecessor, that is 3. And from, okay, we have to create the link to the 1 from its in order predecessor, that is 4. We have to create the link to 4 from its in order predecessor, that is 6. That is the thing what we have, okay, done in this particular tree. Okay, now I have, okay, so this is the code which I have explained for the recursive solution of the recovering the binary search tree using the recursion. Now let us code for the recovering the binary search tree using the Morris traversal. So first, in the Morris traversal, we need a pointer on the, okay, we need a pointer called as current. Let that current points to the root. So we are going to continue the loop until this current is not equal to empty. Okay, so I am saying once again, if you want to study this Morris traversal in detail, you can watch out my playlist. So while current is not equal to null, so this is the condition what I am doing. So if I have already explained, if currents left is equivalent to null, in that particular situation, what we have to do, we have to do some operation, and after that we have to move to our right child. So what's that operation? In order to understand the operation, that is okay, make the first node to point on the previous, and then make the row second pointer to point on the current, and all those things have been explained in the previous video. You can watch out that. So understanding the recursive solution is the most important thing in case of placements. You cannot learn the most optimized solution in each and every question and remember that, and you can attend the interview, means it is completely wrong. So what I'm saying is, if you want to crack the placements in this tree section, then recursion is going to play the most important role in order for your success. So if you write the recursion, then the space is, of course, the space complexity will be compromised, right? The time complexity is going to remain same, as at most we are going to visit the node 2 times. It will be of the order O of 2n. So, and the time complexity is not going to matter that much, but the space complexity is going to matter a lot. So hence, if the interviewer asks you to optimize the solution, then okay, intentionally you write the recursive solution, and the interviewer is going to ask you in order to optimize the solution in that particular case only. You have to come up with a solution which has the better time complexity. Okay, let us understand the solution. Here I have to perform some operation. Here I have to perform some kind of operation. What is that operation? So if the previous is not equal to null and the previous value is greater than the current's value, in this situation I am going to check if the if the invalidation, that is the descending thing, is being found for the first time, then in that particular case, so I'm going to explain it in a short manner because some students will come and they'll try to learn the things directly. So now let us consider the in-order traversal. So that is 1, 2, 5. So 5, 4 and 6 and 3. So I am going to perform the in-order traversal, that is so here I am going to use the previous pointer and the current pointer, and I am going to compare the previous value with the current value. If the previous value is greater than the current value, then I am going to make the first pointer to point on the previous and second pointer to point on the current. But in this situation, let us so create first and second here. So but in this situation, so 1 is less than 2, so it is not a big deal. So hence the current is going to point on this 5 and the previous is going to point on this element. So here also 2 is less than 5, so it is not a big issue. Now the current is going to point on 4 and previous is going to point on 5. And now we are going to compare the data. Here 5 is greater than 4, so hence the first invalidation has occurred. If the first invalidation, so what is the condition for the first invalidation? The first is null initially, and this is the first invalidation. So in the first invalidation, we make first to point on the previous, and so we make second to point on the current, and then we continue the traversal and we will find whether there is any element so which is invalidating the condition again. So now the current so moves on to 6 and the previous points to 4, and so here the condition is satisfied, that is 4 is less than 6. Now we will so move to this 3 and we will make the previous to point on this one, and here the second invalidation has occurred. Now I am not going to update the first, I am just going to update this second to point on the current element, so that I can swap this 3 with 5 and I can get the better results according to me. I can get the better results. So let initially the 3 be here and 6 be here, and this is the basic intuition, that is if you have watched my previous videos, then you can get the perfect understanding of this one. So you must and should, you have to watch the thing. So I have just revised the things very in a quick manner. So if first is equal to null, the first invalidation has occurred, and hence I want to point the first element to the element which is being pointed by the previous, and I have to make the second pointer to point on the element which is being pointed by the current element. Suppose if the first is not equal to null, that is the second condition has occurred, then in that case I have to just update the second pointer and make it point on the current, and this is the thing. And after updating this, okay, and after updating this one, I have to move previous to the current, and after that, so the current will move on to the current's right, and this previous is going to follow the current in the next iteration. So if the previous, that is if the current's left is null, in that particular case, if the current's left is null, then in that particular case, whatever the thing we have to do, I have explained in the above if statement. So if the current is not null, in that case we have to create a predecessor pointer. I have explained this in detail in the Morris in-order traversal video, so please watch that. And I'll make currents left to point on this, and I'm just going to find the in-order predecessors. That is, if predecessor's right is not equal to null and predecessor's right is not equal to current. So why this predecessor's right should not be equal to current, I have already explained, so please go and watch. So this predecessors, I am going to move on to the rightmost element, and I will find the in-order predecessor. After finding the in-order predecessor, suppose if the predecessor's right is equivalent to null, meaning that the link is not present, so hence I am going to make predecessor's right to point on the current, and after making this predecessor's right to point on the current, I just traverse to the left part of the subtree. Suppose if the predecessor's right is equivalent to current, in that case it is saying that the link is already present, then we have to remove the link. So why we have to remove the link? Suppose if you have the same tree and you have to perform the post order traversal. In order to perform the Morris post order traversal, we will use the reverse approach of the pre-order traversal. That means first we will visit the right part of the subtree first, and then we will perform some kind of operations in order to get the answer. But if the links are present and we have not removed that link, then in that particular case you can get wrong answers. Also, if you want to do the operations on the same tree, like in order flattening the tree and all, then you cannot use the links. So that after each and every traversal, completion of the traversal, we have to remove the link so that the original structure of the tree is regenerated and that tree can be used for the other purposes. Okay, I have removed the link here, and I have to perform some kind of operation here, and after performing the operation I have to move to the right subtree. So please watch that Morris in-order traversal video. I have explained in detail. So just copy the entire thing. The operation part is this thing itself. So copy this thing and paste it in between these 2 points, and that's it. So you have completed the recovering the binary search tree using the Morris in-order traversal. Let us run the code and let us check whether this code is going to run fine or not. So as you can see, this code has worked. So I am going to submit this solution. Yeah, I have submitted the solution. So, and it has worked. So don't focus on this time complexity and space complexity, because LeetCode is not going to give the precise time complexity and the space complexity for you, because okay, LeetCode's calculating the runtime and the memory time is quite worst. So you have to do the analysis, and you have to be at such a level that you can explain time complexity and analyze the time complexity on your own. So thanks a lot.